Okay, could you see it now? And can you hear me well?
Yeah, we can see and hear well. Okay, everything's good.
Good, thank you. So what I want to do today in this lecture is to give you a more general talk to discuss a bit about the theory behind the many-body Green's function approach to excited state properties in materials. And I will give you some examples on quasi-particle excitations, optical responses, and field-driven time-dependent phenomena. And some of the details of the method and our BerkeleyGW code will be covered by other speakers in the today and tomorrow. So as you all know, the study of material properties is basically an n-particle quantum problem with the electrons and ions interacting with each other. However, here n is very large. For a macroscopic sample is in the order of 10 to the 22 per cubic centimeters. So it's impossible to solve the problem exactly for the electronic properties. This is also the reason why our field is so rich. In fact, it's often not desirable to get the full solution because the full solution will be very, very complicated. So it is actually better to focus on some physical quantity that are of interest so that you could make approximation to it. So for example, you're interested in single particle like behavior, such as those measurements in, say, a tunneling experiment, then one would be more interested in finding out what the probability of finding a particle at position r and time tau when a particle is introduced at position r prime and some earlier time t equal to 0. So this is, in fact, the interacting single particle Green's function that you learn in textbooks. So this is what we call n+1 particle problem, looking at particle-like excitation in a otherwise strongly interacting many-body system. And if you're interested in optical properties, then one would be looking at a n+2 particle problem because when the photons absorb, you create an electron and a hole. What we're interested in is, in many cases, like excited state phenomena, such as those you measure in transport, optical, energy transfer, or charge and spin dynamic processes. And these are important because very often this kind of properties give rise to the defining attribute of a material and determine how useful it is. However, ab initio calculation of excited state properties often require a different and higher level of treatment of many electron interactions, for example, compared to that of DFT calculations. As you might be aware, there are now existing many ab initio methods and community codes for predicting and understanding one or two particle excitation in increasingly more complex materials. Here I listed the name of some of the codes that are available to users in the community. There are, however, key phenomena such as 3 or 4 particle correlated excitations, nonlinear spectroscopies, field-driven processes, and excited state dynamics that still need to be addressed more carefully by ab initio method and public domain software that includes the relevant many electron interaction at an accurate enough level. So in today's talk, I'm going to basically talk a bit about how BerkeleyGW address this set of problems. So this is the outline of the talk. I will begin with a brief introduction to many-body interactions and excited state phenomena. in materials. And then we're going to talk about quasi-particle excitations, optical responses, and correlated multi-particle excitations. Next, we're going to discuss some time-dependent and high-field phenomena, and then talk about correlation enhance the electron-phonon interaction. And finally, if I have time, I'm going to give an example of how the photophysics of a 2D Moiré system can be different from that of a box system. So when you include many-body interactions, then, for example, if you want to look at a particle like excitation in your material, then the energy dispersion of that particle is now modified because of the many-body interaction through a term we call the self-energy, which Professor Justino has already talked to you guys about in terms of electron-phonon interaction. And this kind of self-energy term will renormalize the energy dispersion of the quasi-particle, and that gives rise to finite lifetimes and sometimes even prominent satellite structures. So, for example, if you were to do a photoemission experiment, then the probability of creating a hole in your measurement will be given by this self-energy through expression look like that, which involve both the imaginary part and the real part of the self-energy. And the self-energy can have many contributions, electron-electron interaction, electron-phonon interaction, and so on. And today I'm going to focus on the electron-electron contribution to the electron self-energy. And you already heard about how electron-phonon interaction contribute to the self-energy in the last few days. So within the Green's function approach, the self-energy can be calculated through many-body perturbation theory in a Feynman diagram expansion of increasing order involving the appropriate interaction. So here we're going to look at the electron-electron interaction. It turns out that it's much more efficient to expand this perturbation theory in terms of the screen Coulomb interaction, W. That is the bare Coulomb interaction screened by the dielectric matrix of the system, as opposed to the bare Coulomb interaction, because the screen interaction is much weaker than the bare interaction in general. And it turns out that for many material, not all materials, it's really sufficient for the electron-induced self-energy to just take the first diagram in this expansion. And this is called the GW approximation. One could do the same trick also for the interacting two-particle Green's function to obtain the optical property. If you do that, this is called the GW beta salpeter equation approach, then you could get out the linear optical properties, including excitonic effects. So to get the quasi-particle properties of a crystal, one then solve a kind of a single particle-like equation. We call that the Dyson's equation. Look very similar to that of the Kohn-Sham equation, except that you replace the exchange correlation potential by this self-energy operator. And within the GW approximation, that is taking this first term, then this is explicitly given by the one particle Green's function and the screen Coulomb interaction. Now, to form the self-energy operator, one need to know the interaction and also the Green's function. So the required input to such calculation involve the full dielectric matrix which is non-local and frequency dependent for the material, and also a starting point for the wave function and energy to construct the Green's function. So the spirit of this approach is that of perturbation theory. You start with some kind of mean field plus a perturbation due to the true Hamiltonian minus the mean field. So the mean field 0, 0, H0 can be any kind of starting point, Hartree-Fock, DFT, and so on. It turns out that with DFT, for many material, that's a very good starting point. And one can try to iterate the Green's function with the solution for the Dyson equation. Now, for the optical absorption spectrum, what we need is then the two-particle electron-hole excitation in the system. And because the electron and the hole interact with each other, such excitations are linear combination of free electron-hole pair excitations. And the wave function is given of this form where A tell you the coefficient that couples the different electron-hole pair excitations. One actually can determine this coefficient A and the energy for the excited state by looking at the two-particle Green's function and via the so-called beta-salpeter equation. This equation is given by the expression right here. It's an effective two-particle equation where epsilon is the quasi-particle energy, which you could get out from the GW calculation. And then K is the electron-hole interaction. So by solving this equation, you get out the excitation energy and the wave function of the correlated electron-hole states. And once you have that, then you could calculate, say, via Fermi's golden rule, the absorption spectrum and also the optical property of a material. And the Coulomb hole, the electron hole interaction, K, in fact, can be derived from the self-energy of the electron and also the Hartree interaction. And that leads to a repulsive interaction between the electron and hole, and also attractive interaction between the electron hole. The second one here, we call that the direct interaction, and the first one is an exchange type of interaction between the electron and the hole. And this K is a very large non-Hermitian matrix, just like the self-energy, and it in general requires a very fine K-point sampling. And K can be in the order of a million or more for a typical material. So let me show you some results for this kind of calculation. Here on the left is a comparison between the calculated band gap of a range of insulating material compared to the experimental band gap. Typically, as you know, Kohn-Sham eigenvalues underestimate the band gap of insulating material. And within this GW approach, even at the first order level, you get a quite good agreement between theory and experiment. And on the right here is the optical spectrum, epsilon 2 of omega for silicon. The blue line is calculated with within the kind of interband transition picture. That is no interaction between the electron and hole using the GW band structure. And then the red line is when you solve the beta-salpeter equation, that is solving the interacting two-particle Green's function. And then the dots are the experimental data. So you see that electron-hole interaction has a dramatic effect on the optical spectrum, even for a material like silicon, where the electron-hole binding energy is very small. And in fact, at a low frequency for the absorption, the the oscillator strength is enhanced by more than a factor of 2 due to electron-hole interaction. To give you an idea how much progress has been made over the last decades regarding to this kind of calculation, I show you the number of the number of electrons that you could treat within the GW method as a function of years. These are looking into the literature and just look at what the biggest system one has able to compute over the years. You see that in the 1980s, we could only calculate a system like silicon gallium arsenide, so it involves about 8 electrons per unit cell. But nowadays, we could get to system with thousands and even tens of thousands of electrons. Now, let me go into some of the physics and then show you how important non-local screening and correlation effects are for looking at quasi-particle excitation and optical properties. I'm going to use the example of quantum level alignment at the interface. For example, you're putting a molecule on a metallic surface. How would the molecular levels modify because of the presence of the interface? And these are very important because the molecular levels will come into a lot of phenomena that is of importance. For example, transport through such an interface or optical absorption at an interface. And in general, you would expect that as you move the molecule toward the metal, the molecular levels, the HOMO and LUMOs, will be modified. They will be shifted and then broadened through interaction effects. And in general, you're able to think about this in terms of several processes. One is interfacial charge transfer, forming some kind of dipole, quantum mechanical coupling, hybridization effects, and then electron correlation effects. It turns out that all three of them are very important. In particular, for weakly coupled systems, the correlation effects can be very important. So let's look at the case of a benzene on top of graphite. So you do a DFT, LDA, or hybrid kind of calculation. What you find is the molecular levels will be not very much change from that of an isolated molecular levels because the molecules is at a van der Waals distance away from graphite. And from a DFT, LDA calculation, you will see a HOMO-LUMO gap of around 5.1 electron volt. If you do the same calculation at the GW level, you will find that the gap is, the HOMO-LUMO gap is quite increased, but very much increased to 7.3 electron volt. And it's greatly reduced from that of isolated molecule, which has a calculated gap of 10.5 electron volt compared to the experimental value of 10.4 to 10.6. So you see that the environment makes a big change in the HOMO-LUMO gap. It can modify that by few electron volts, which was not able to capture by the Kohn-Sham eigenvalues. So in general, change in the self-energy can be quite large and due to environmental effects and could be in the order of 2 electron volts. And this set of example also shows a clear importance of correlation effects. So this is a similar type of study, benzene on surfaces, but with looking at different surfaces. And if you do an LDA calculation, you get a particular value of the gap, and it doesn't change much from one surface to another surface. even if you do a hybrid functional calculation, you get a different gap, but it doesn't change from one surface to another also. If you do a GW calculation, you find a very different result. For the same molecule, you have completely different homoluminal gap depending on which surface you look at. In fact, that's the case what you find in experiment. In particular, if you look at the barium oxide surface, two different surfaces, 001 versus 111, you will see that there's a dramatic change in the band gap because one of the surface, in fact, has a surface state, make the system more metallic-like. So there are strong and different renormalization of molecular levels with different contacts, which are absent in the Kohn-Sham or orbital energies. Now, to illustrate this point a little bit more, let's look at reduced dimensional system and look at how interaction changes the optical property of the materials. As you know, when you are in reduced dimension, you have increased Coulomb interactions. But one lesser known fact is that you could also have very strange and strong spatial screening dependence for such system. This is illustrated here by this cartoon. When you have two charged particles interacting, they interact via the Coulomb line, and you see that some of the lines actually go outside of your sample because you have a 2D material. So in fact, when the two particles are very close to each other, the interaction is not screened. And when they're very far away from each other, which is also unscreened because the field lines go outside the sample. This is very different from that of a bulk material. And if you put this sample on a supporting surface, say, then you see the field line could go into the substrate, and then the interaction will be modified. So you expect in general, the excited state property of a 2D material would be very strongly dependent on the substrate and environmental screening. So let me give you one example regarding to the intrinsic excitonic effects in 2D material, and then later I talk about the environmental effects. So here's it's looking at the case of the optical spectrum of monolayer moly disulfide. The band structure of this material is given here. It's a semiconductor with the band gap at the K and K prime Wally point. The top here is the calculated absorbance as a function of photon frequency, done either neglecting electron hole interaction or including it through solving the GW beta salpeter equation approach. And you see that the dramatic difference between the two optical spectrum, they're qualitatively different from each other. And in the case when you include electron hole interaction, you actually see a series of big peaks inside the band gap corresponding to strongly bind excitons that correspond to each of these kind of interband transitions. And each one of these transitions gives you a series of excited excitonic peaks. And the exciton binding energy, in fact, is very large. It's in the order of a fraction of electron volt, which is typically a couple order of magnitude bigger than that of the exciton binding energy in bulk semiconductors with the same band gap. And how's that compared to experiment? This is the experimental absorbance done by Mac AL at Columbia at the time. And you see that they do see very strong excitonic peaks and very large absorbance at higher frequency, corresponding to this kind of formation of exotonic states. And in this calculation, we neglected the electron-phonon interaction. But if you include that, then you get this green curve here, which is even in better agreement with experiment. And this kind of many-body interaction effect, electron-hole interaction, dramatically creates new states and also changes the oscillator strength. It robs some of the oscillator strengths from higher energy excitations to lower energy excitation. In fact, the absorbance of a half a nanometer of this material is in the order of 20%. That's very large. Compared to our bilayer graphene is about 5%, and silicon is only about 0.02% because it's an indirect gap material and it's a bulk system. And the individual energy level of the exciton, in fact, is very different from that of the bulk also. Here is the initially calculated excitonic levels for the A transition here at the K point, K valley. And what you see is very strong binding energies for all the states. And what's even more interesting is that the higher angular momentum states, in fact, has lower energy of the low angular momentum state. That is somewhat surprising, because if you were to do a kind of a textbook hydrogenic model calculation for this system and fit the dielectric screening to arrive at the 1s level of the exciton to agree with the ab initio calculation, you will get a result given here. And the reason for this qualitative difference is that because screening in 2 dimensions, as I mentioned, is quite different from that of the bulk. So here is the affected dielectric screening as a function of distance on your layer, and you find that screening is very ineffective at large distance. So that means that the higher excited states with larger excitonic wave function will be weakly screened. Therefore, they would have bigger binding energy. And in fact, the 2p states would have a bigger radius than the 2s states, and therefore explains this angular momentum dependent on the binding energies. Now let me turn to a bit about substrate screening. Here, to illustrate that, I look at monolayer molybdenum and look at the screening charge due to having a metallic substrate. So here is the induced screening charge when I put a negative point charge at this point here. So the screening charge due to the substrate, in fact, is quite large and complicated. And this is because screening is non-local and frequency dependent. And one really has to incorporate this kind of screening if we were to look at the optical property or the quasi-particle property of a 2D semiconductor. In fact, we and other people have found that for some systems, substrate in encapsulation due to this kind of screening effect to the self-energy can normalize the band gap by more than 50% and change the exciton binding energy by a factor or more, 2 or more for typical 2D semiconductors. And it can also modify the property of other excitation in the material. For example, for metallic TM transition metal dichalcogenide systems, you have long-lived plasmons, and the energy of those plasmons can be changed by order of magnitude depending on what substrate the system is on. So this kind of example I gave you can be now calculated through the BerkeleyGW package. The speakers after me in today and tomorrow going to give you more detail about the BerkeleyGW package. So this package is a general excited state phenomena code that supports GW and GW beta saltpeter equation calculations for 3D, 2D, 1D, and molecular systems. It supports insulating metallic and semi-metallic systems. It interfaces with a large set of DFT and other mean field codes. It's massively parallelized, making use of high-performing performance computing facilities that could scale linearly up to 500,000 CPU, for example, at the NERSC Center, and to about 30,000 GPUs at the Summit machine at Oak Ridge. And it could give you accurate solution to the beta saltpeter equation via very fine K-point samplings up to about 1 million K-point. And this is very important to study photophysics, including correlation effects. For example, recently we have done calculation on a large system that contains about 3,000 atoms, looking at defects in semiconductor. Now let me return to non-equilibrium and beyond 1 and 2 particle excitations. In order to understand this kind of new phenomena, one needs to have different ab initio formulation going beyond the standard GW and GW beta saltpeter equation approach. For example, if you're interested in looking at correlated higher number particle excitations, such as trions, that is an exciton plus a charged particle, bi-excitons, 2 excitons bind together, and so on, then in fact, you have to solve now the interacting 3 and 4 particle Green's function. You're interested in looking at time-dependent and high-field phenomena, such as pump-hole experiments, nonlinear optics, and so on. Then one need to now look at the explicit time-dependent of the Green's function. For example, calculating the time-dependent Green's function within the GW approximation using non-equilibrium Green's function approach. So let me first give you some example of correlated multi-particle excitations in 1 and 2 dimension. Since electron interaction is enhanced in reduced dimensional system, it's not surprising that the multi-particle excitation becomes more prominent in the atomically thin 2D system. The example I give here is for bi-excitons on monolayer tungsten diselenide. What's shown here is the photoluminescent intensity as a function of at different fluence of the excitation light. And what you see is this peak here labeled XX that changes with the fluence intensity. This peak, in fact, has been identified as a bi-exciton and studied quite well experimentally. And this kind of phenomena, in fact, are also of fundamental and practical interest in other areas, for example, exciton condensates or splitting of a single exciton into 2 inorganic crystals for photovoltaic applications. So how do you go about calculating, for example, a bi-exciton state? So as I already mentioned, for quasi-particle excitations in the GW approach, you need to solve this one single Feynman diagram. For optical excitation, including electron hole effects, then you have to solve there's two Feynman diagram within the GW beta salpeter equation approach. For bi-excitons, which is a 4-particle correlated excitation, within the interacting Green's function approach, one now have to solve 36 diagram of this kind, which involves 4 particle lines. This seems very complicated, but it's actually doable. We have developed the formalism and the computer codes for such calculation recently. So let me give you the example of the case of monolayer tungsten diselenide and look at how the bi-excitons behave in such a system. This material is also a semiconductor. It has a band structure very similar to that of monolayer molybdisulfide. The low energy states are at the K and K prime valley, and the wave function and the band structure and the wave function of the two valley, in fact, are related via time reversal symmetry. So you could form bright intra-valley excitons. You could form a dark intra-valley exciton, or you could form even a dark inter-valley exciton, as indicated here. And these excitons could capture a carrier and then form trions, or they could combine together and form bi-excitons. Here's some of our result using the interacting Green's function approach, comparing the binding energy of the trion and the bi-exciton with experiment. And so here are the binding energy, basically calculating with no adjustable parameters. They compare actually quite well with experiment. These are, in fact, the first fully ab initio many-body calculation of this type. Our results show that they have very rich energy and spin valley level structure. In fact, these are high temperature phenomena because the binding energy are very large in the order of tens of milli electron volt. The theory, in fact, elucidates the experimental observation and, in fact, gives some new predictions. For example, the binding, the bi-exciton in this system, traditionally, it has been assumed to be of this form, that is a bright intra-valley exciton combined with a dark intra-valley exciton. But according to our calculation, the measure exciton, a bi-exciton, in fact, is not of this type, but is formed by a bright intra-exciton together with a dark inter-valley exciton. And this kind of configuration was ignored previously because of the neglect of the importance of the electron hole exchange effect that one could include accurately in our four particle Green's function approach. Now let me turn to field-driven time-dependent phenomena. Here, what we need is to have knowledge of the time dependence of the interacting single particle Green's function. And to do that, one has to use a non-equilibrium formalism, that is solving for the Green's function on the Keldysh contour in the presence of some driving field. By doing this kind of calculation and doing real-time propagation, one could now get our linear and nonlinear responses and time-resolved phenomena with self-energy and exciton effects included. For the experts in the audience, the method we developed is based on the initial time-dependent GW approach within the adiabatic approximation just like the adiabatic TDDFT approach, with real-time propagation of the many-body density matrix. So let me give you one example. That's shift currents in materials. Shift current is a photo-induced DC current in non-central symmetric crystal without having a PN junctions. So this is called the bulk photovoltaic effect. It's a second-order optical response. That is, you get a DC current in the presence of an optical excitational field. And in fact, it's related to the band topology of your material. That is to the shift of the intershell coordinate of the electron from the optical transition. Here is our calculated result using this TDAGW approximation for monolayer germanium sulfide. Plotted here is one of the coefficient of this shift current tensor as a function of photon frequency. The blue curve shows the case when we neglect the electron hole interaction in the simulation, and then the red curves are when we do the full simulation, including the electron hole interaction. So you see that the excitons, in fact, enhances the shift currents by orders of magnitude, huge. And what's even more interesting is that you could get charge transport within the band gap with CW in-gap excitations. So this is very interesting because it gives you the possibility of using this kind of bulk photovoltaic effects for solar cell applications without having to have PN junctions with 2D materials, because exciton effects are so strong in 2D material. In fact, if you look at other second-order processes, such as second harmonic generation, you find that excitons also can greatly enhance those second-order responses. And here's an example. This is a case of looking at Chi2, the tensor for second harmonic generation for monolayer germanium sulfide, and comparing neglecting electron hole interaction with including electron hole interaction. So you see that excitons can, in fact, enhance it by orders of magnitude at certain frequencies. One could also use this kind of approach to look at time-dependent phenomena. So here I give the example of field-driven phenomena in time-resolved, angle-resolved photoemission experiment. Normally, you think about studying excitons and other excitations through optical means, but we and others recently have realized that you could actually study excitons through time-resolved, angle-resolved photoemission measurements. The idea here is that you pump the system with optical light to drive it to a non-equilibrium state, and then you probe it with another beam of light later to a Hoppus measurement. So here is the example of monolayer germanium sulfide again. Here, what we do is simulate the experiment by pumping the system with an optical light at resonance with excitation energy of the system, and then probe it later through angle-resolved photoemission procedure at a delayed time. So this figure shows the spectrum, the Hoppus spectrum in the case when we neglect electron-hole interaction. So what you see is a spectrum look very similar to what one expected. These are the occupied bands. And you see some of the unoccupied conduction band because of the pump pulse excitation. Now, on the other hand, if I include electron-hole interaction, then what we find is new features near the conduction band. And those new features, in fact, correspond to excitons. You get a series of excitons near gamma and a series of excitons near lambda as given by the GW beta salpeter equation calculation that you could normally do. Here, by just looking at this spectral function, we actually now could get out the exciton energy by looking at this energy difference and the exciton wave function by the spread of the feature in K-space. That is this coefficient A that I mentioned earlier. So this kind of experiment, it's doable now, and it has been performed in the last couple of years by a number of experimental groups. You could now get out directly the exciton energy and wave function of the system. And in fact, you could see that in the presence of the pump light, you could have also a renormalization of the quasi-particle bands due to many electron interactions. Now, in the last 5 minutes or so, let me finish up by saying a few words about how many electron interaction can change the electron-phonon coupling, and also one example about Moiré physics excitons. You have already learned in the last few days electron-phonon coupling, which is a very important quantity in understanding many phenomena. In the standard kind of DFT approach, the electron-phonon matrix element you calculated, in fact, is for that of the non-interacting cone-sham orbital with the phonons. Now, this kind of approach is very accurate and good for a number of materials. However, it's also known that it can fail for some materials. So what we have done recently, this is work that Professor John Louie have worked on, and he will give you more detail in his talk later. What we have done is to include self-energy effects on the electron-phonon matrix element at the GW level. That is, in the calculation of the matrix element G, we take away the contribution that due to the exchange correlation potential from a standard calculation, and then replace it with the contribution due to the self-energy at the GW level. It turns out that this kind of self-energy effect can renormalize G by a large amount, by as much as a factor 2 in some materials. So here is some results. This is comparing calculations done using the DFPT method, and that with this GWPT method, which is also a linear response method for the electron-phonon coupling constant for a number of material. You see that for most common normal metals, the two approaches give you quite similar results, almost exactly the same results. However, for some materials like bismuth, potassium dope, barium bismuth oxide, an important transition metal oxide system, you see that the self-energy can enhance lambda by a factor 2. And this kind of enhancement, in fact, explains the high transition temperatures, superconducting transition temperature in this material, and also the dopant dependent of TC for this material. We have also applied this kind of approach to look at other oxides. For example, we were able to explain the photon emission king in the clip plates, and that king is completely underestimated within DFT-PT, but can now be explained quite well by a GWPT approach. In the last couple minutes, let me mention some work we've done on Moray superlattice of twisted bilayer systems. There are many exciting new physical phenomena have been observed in this kind of systems, including flat bands, unconventional superconductivity, correlated insulating states, and novel Moray excitons in this kind of systems. So let me show you just some results on the intra-layer Moray excitons in the tungsten diselenide, tungsten disulfide bilayers. This two layers forms a type 2 band alignment interface. And if you look at the refraction contrast measurement, these are data from Fang Wong's group at Berkeley, what you find is a large twist angle in the region where you observe intra-layer excitons. Then you find a single peak corresponding to the so-called A exciton in a monolayer. However, if you twist, make the twist angle very small, then this exciton split into 3 different excitons. And the question is, what is the origin of this splitting and the nature of the exciton? An early theoretical understanding of this kind of Moray intralayer exciton is through what we call a continuum model. In this model, one assumed the exciton sees an effective potential due to the Moray formation, superlattice formation, and it is modeled as the spatial variation in the intralayer band gap as a function of the changing layer stacking. However, within this model, there are 2 important physical assumptions. One is that the model neglects a structural reconstruction of Moray superlattice. And the second one is that one assumes that the internal structure of the exciton is identical to that of the pristine monolayer. It turns out that both assumptions may not be valid in many cases. For example, looking at this particular case, because of the mismatch of the lattice constant of the 2 material, it caused a Moray superlattice reconstruction, and such a reconstruction gives rise to a strong, large strains on the atomic positions, and that lead to flat and gapped Moray subbands with different characters. And this is important. It turns out that that's the origin of the splitting and give rise to some very interesting physics. Here's our calculated ab initio result to a beta sub-beta equation formulation, and this is experiment. So you see that there are now quite good agreement with experiment, and one could look at the character of the wave function of the exciton in the various peaks. For example, for exciton 1, we find that the electron, in fact, follows the hole. So it is all the kind of a linear exciton, but modulated by the the Moray superlattice structure. However, for exciton 3, in fact, the exciton has a very, very different character, which cannot be described by a continuum model. It is of a novel charge transfer exciton character that does not exist for a monolayer. And this charge transfer exciton has a very large radius in the order of 5 nanometer, even though the binding energy is still very large in the order of fraction of an electron volt. And this is basically come from having flat band and strong modulation in the potential seen by the quasi-particle in the system. So within the continuum model, you will get a spectrum like that, all the electrons of the 1A type, but within the ab initio GW beta salpeter calculation, you have a very different spectrum and very different kind of character for the excitons in the system. And this kind of effect, in fact, should exist for all Moray systems. And it gives rise to a number of experimental signature, which have been also verified experimentally by my colleague Fang Wang at Berkeley. So let me, since I'm running out of time, let me conclude by giving this last slide, a few take-home messages. So I hope I convince you that many-body interaction are centrally important in material property and phenomena, which I think all you know already. And the treatment of interaction effects at the appropriate level is essential, especially for excited states and lower dimensional systems. And many-body perturbation theory will screen the Coulomb interaction to the n-particle interacting Green's function has proven to be a powerful and versatile approach for the understanding and prediction of a number of spectroscopic property and field-driven time-dependent phenomena in real materials. So thank you very much for your attention. I'd be glad to answer some questions.
Thank you, Professor. Thank you, Professor Louie, for giving a wonderful talk. So we have several questions, and we will have some time to answer them. I will read the questions in the Q&A box, and you can answer them. So the first question is, why are the derivatives of the screened interaction with respect to the Green's function ignored in the electron-hole interaction in the BSE formulation?
That's in the, this is regarding to when you're taking the self derivative of the self energy, right? So what's happening is that the screening in general is not so sensitive to the exact Green's function, as long as you have a reasonable description of the dielectric function of this system. So in general, you could think about that change is very small, and numerically, when we first formulate the GW beta salpeter equation approach, we have tested and so that change is very small. So that's one justification. That is, in general, screening doesn't depend on the detail of the charge distribution or the character of the wave function, orbital wave function. The second thing is that through the experience in the last 2-3 decades, comparison with experiments, so that this is a very good approximation. But of course, this approximation is an uncontrolled approximation. It's basically or you do it because it would be so complicated to calculate that turn.
Thank you. Next question. When constructing the exciton states and thus the BSE Hamiltonian, if V and C are all restricted to the unoccupied manifold, which means it represents the 2 electron excitation, do the corresponding BSE eigenvalues mean anything that is physically observable?
I'm not, could you repeat the question?
Sure. So when constructing the exciton states through BSE Hamiltonian, so we have V and C bands. The question is asking, what if the V and C bands are actually all the unoccupied bands? Would that represent the 2 electron excitation or some other excitation that can be physically meaningful and observable?
You mean having V and C are both unoccupied?
Yeah.
It does not come out naturally from the formulation. You have excitation and de-excitation in the full formalism. So V and C come in pairs through the fact that you're dealing with a many-body wave function, which is a Slater determinant. So I don't think that would naturally come out. In the time-dependent Green's function approach, you do have terms like CCVV, and that's because as time evolves, the occupation of the valence bands and the conduction band changes.
Thank you. Next question, I try to rearrange the wording. So in the example of MOS2, the band gap value is different from the absorbance edge. In this case, it represents the exciton binding energy, which is 0.65 electron volt. How is this binding energy calculated?
This binding energy is calculated through solving this effective 2-particle equation. So it's quite accurate because it's just like solving the hydrogenetic model where your single particle states, you have an electron attached to a proton, you know exactly where the continuum edge is, but solving the hydrogenic equation gives you an answer to the binding energy directly. So the binding energy come out from the solution of the beta salpeter equation. I hope this answered the question.
Thank you. So because of time, I'll probably just read a few other questions, and the rest of the questions, Professor, if you want, you can answer them by typing the answer. Another question is, what is the difference between dark and bright excitons? Is it related to electron spin orientation?
Yes and no. I mean, yes, there are lots of dark excitons are not, there are a lot of excitonic states are not optically active because of spin configuration, that is, absorption of a photon cannot really flip the spin. So that's one answer, but there are also dark excitons because of orbital selection rule, just like in the hydrogenic atom case, you do not have transition from 1s to 2s because of orbital selection rules. So the dark excitons that I presented in the Mali disulfide slide is those darkness come from orbital selection rules. So
Thank you. I will read one last question. So what kind of correlation effects in such a strongly correlated system cannot be explained by GW approximation or GW plus BSE. GW is named as many-body perturbation theory. Does the perturbation mean the self-energy correction is much smaller than, say, for example, the Hartree energy?
Well, it's perturbation means that you're expanding things in higher and higher order of interaction, and that's what the word perturbation comes in. I think to answer the first question is that GW gives a very good treatment of long-range interaction, charge fluctuations. So if you have very, very strong local correlation, like in the highly correlated electron systems, then you need to take diagrams that are different from that of the GW diagram, the first diagram in the series I put down. So if you have very strong local electron interaction, then GW tend to give you not accurate results. But other theories like dynamical mean field theory, in some sense, is also perturbation theory.
Thank you. So because of the time, I think I'll finish reading the questions. The remaining questions can be answered by typing the answers. So let's thank Professor Louie again for the very nice talk.